Hi everyone, and welcome back to a new video about system identification of a first order system. This is our example number 3. In the example we'll again look at our calculation step by step and verify this calculation using MATLAB simulations. So let's look at the example. What we have is the following unit step response given on the right side, and we would like to determine, as we did in the previous videos, the transfer function. So that's what we are heading. In this case, it is different than the previous two examples. What we don't see here is the steady state value of our response. So that is not really determined or not clear from this plot. That can happen. That might be a possible option or possible result from your measurement. What we do know, or what we can determine, is our 2 points from our output response. So we have a unit step input, that's why it's called unit step response, and the output shown here doesn't have a clear final or steady state value. So how can we then tackle this? Now I have already placed 2 measurement points. You can of course take another point if you want for more accuracy. And we will use these points to determine the transfer function in this exercise. So let's look at our solutions. So the solutions, again, we make observations from the graph, and if I look at the output response, that's what we see here, we can see that this slope has again a value which is larger than 0, and this shape is again very similar to a first order system. Now in this case I assume, and I can then use the approximation, that this is a first order system, since the slope here at the origin, at the start, is non-zero, it's positive, and it has a shape of a first order system. Again, as I said before, I have determined at, for example, time equals to 1 second, that the value is 4.36. Another point at 2 seconds, so that's also written actually like this, C, which is then our output, at time equals to 1, it's equal to 4.36. Now for at time equals to 2 seconds, I have a value of 5.79, and again as shown here, and I can also write that down in a different form. C at 2 seconds equal to 5.78, I mean. So what do I do now next? I of course want to have a transfer function, so let's first look at the transfer function model of a first order system without a zero or delay. Then we have the following model. We have the h, which is then our transfer function, is equal to kdc, which is the dc gain, over 1 plus the tau s. In this transfer function, the kdc is called the dc gain or the steady state gain of your system. The tau is the time constant, and which is expressed in units seconds. That's what we need to use for our transfer function. So we have 2 parameters we need to determine for our transfer function. Remember, as I said before, and I will repeat it again, the kdc here is not the final value of this response specifically, it is the gain of the system. And in this case, since we have a unit step input, that means the height of your input has an amplitude of 1, then the kdc is equal to the value of your steady state value of your output. That's only in this special case. So let's look at the transfer function then for the system. Now the general form of our first order response, step response, is shown here. Again, the output C as a function of time is equal to the C at infinity, that is actually the steady state value, minus, between the parentheses, the steady state value minus the initial value times e to the power minus t over tau. So we have actually 3 unknowns, which are the final value or the steady state value, the initial value, and the time constant. And I of course need the time constant in my transfer function, which is given here in the Laplace domain. So what do I know? I know from my graph, if I look at my graph, the response, that the initial value is 0. So at 0 I have a value of 0. So I can say C at 0 is equal to 0. So this is already known. Then I can say the following. Let's then substitute these 2 points in this expression. So the first point, c at 1 is equal to 4.36. Then I have the following expression. I have of course already substituted the value of the initial condition, which is just 0. Then I have the following. Of course, for time I just substitute 1. And this is the expression I have from my first measurement point. In a similar form, I can do that for, of course, I can rewrite this in this form, so I can then have a little bit simplified format. In a similar form, I can do that for another point, which is then at 2 seconds, and I have a value for 5.79, and this is then the expression I have, again, at 2 seconds, and again, the initial value is 0, it's equal to 5.79. And I can then rewrite this in this form. It will be compact. So I can see now 2 equations. I have this equation number 1 and also this equation number 2. And I will use that to determine the tau, which is then a time constant for this system. And then I will use that tau to determine the KDC. That's actually the next step. What I see here is I have 2 equations and 2 unknowns actually, because this is the C infinity, this is actually this DC value, or I mean the steady state value. That is also here, and I have a tau and also here. So I have 2 unknowns, same unknown here and unknown there. So I can solve this using substitution or another method. So let's look at the following situation. Writing the first expression, this expression in this form, so as C infinity, so the DC value or the steady state value of your output, isolate that and then write it down in this form and substitute this expression in here. I have the following. So first expression, rewrite it in this form, substitute that in the second expression, which is shown here, then I have the following. What do you see? I have actually only tau as an unknown. So if I now rewrite this a little bit, just place this underneath here and then place this in the numerator. I have this, and this has a ratio of 1.33. Okay, if I just simplify that even further, I have this expression and then get in this form, which has a 0 at the left hand side or right hand side, what you prefer of course. Then you have this expression. So we need to solve this in order to solve of course the value for tau. So let's look at it in the next steps. This is what we had determined in the last step. This is our equation we need to use to determine the tau. What I can do here is make a substitution or make a setting as p is equal to e to the power minus 1 over tau. If I do that, I have the following. This will be p squared. This will be just p, and this of course is a constant, so I have a p squared minus 1.33p plus 0.33. And if I now place this in fractions, I have then the following. I have p minus 1 times p minus 0.33. Now if you work out of course the parentheses here, you will get exactly the same result here. So this now already says that the p or p1, so one of the solutions for p is 1, another solution is 0.33. But which of these are or is valid? We need to determine that of course, because the p is here is already defined as e to the power minus 1 over tau. We can see what value of p will be valid. If I have now for p is equal to 1 and I use this expression, then I need to have e to the power minus 1 over tau 1 must be 1. So the tau 1 must be then minus 1 over the ln of 1. But that will go to infinity. So that is of course not really valid, because you cannot have an infinite time constant. That will mean that the response is infinitely slow. So this is not valid in this case. Now if I now look at another solution, which is then the following for this one, I have this, so it is then 0.33, again tau 2, and expressed in this form, so 1 over minus 1 over ln 0.33, I get 0.902 seconds, which is valid, which is perfectly fine. And then your tau, the the controller model, the system model has a tau of 0.902 seconds. That's actually the tau we will use. So that means actually the next step is then calculate the remaining part, which is then the C at infinity, or the KDC actually in this special case, which is then the steady state value of the output. Now, as I said before, and again, a repetition here, since the input is a unit step, has an amplitude of 1, the steady state value of your output is equal to the steady state gain of your system, which is the KDC. So, C at infinity is KDC. That is what we can say here. Then we have the following. I can say this is already determined in the previous discussion. We have from the first expression, the C at infinity was 4.36 over 1 minus e to the power minus 1 over tau. And if I use specifically the tau 2 here, in this expression, I can then determine the C at infinity, which is then the KDC, which is then 6.51 in this case. So I have now the tau and also the KDC value. That is those are the required two parameters. So having calculated all the required parameters, I have this. And if I just rewrite this, I have this expression, and I can see directly here that the pole is at minus 1.11 approximately. So this is actually the pole. And of course we will use this to check the result, the performance of our system in the simulation. So let's look at the next step, which are the simulations. So the simulation result, transient response, in this case the unit step response. So this is the unit step response, what we have, and this is just simulated in MATLAB, and this is what we had given, which is the unit step response. This is the output, of course, and the input is, of course, since the unit step has a step input of 1 as an amplitude. What you see is at 1 second I have 4.36 is exactly here. So that's also these values. So I have this transfer function. So I can see the first point is correct. The second point is here at 2, I need 5.79, and it has a 5.8, which is very close to what I have. So this might be due to the rounding of errors, but that is very close to what we actually have. I also see that the final value is 6.51, which is actually shown here. How can you determine actually the final value in here? You just substitute for s is equal to 0, this will go. Then I have 6.51 over 1 plus 0, which is just 6.51 over 1, which is just 6.51. And that is now our DC value. And this is the confirmation in your unit step response for this plot in MATLAB. So that's correct. So we have verified now our transfer function of a system. Of course, let's also check that in Bode plot or Bode diagram. What we see is the following. This is our transfer function again, and rewritten in a different form, which will be helpful in this case, is this. We have also this expression previously determined, and we can see the pole directly at minus 1.109. Now what you see is that the gain of your system at approximately DC, which is not exactly DC, but it is very close to a very small number, of course, then I have a magnitude of 16.3 dB, which is then the gain at approximately DC. So DC gain can be calculated using this formula 20 log base 10, actually this, so it is at base 10, and I just fill in this value, which is the KDC, DC gain of our system. I get 16.3 exactly in dBs, and that's a confirmation also here from the simulation. What I also see is, if I want to determine the cutoff frequency, in this case since it is a low pass filter, and also the bandwidth, I can see if I go down by 3 dB of this DC value of this response, I get a 13.3 dB, and I can see that this will be at the frequency of 1.11 radians per second, which is then this frequency. So the pole frequency of a first order system is also the cutoff frequency of your system, and that's actually the confirmation. What you also see as an additional confirmation that the phase at that same frequency is minus 45 degrees. This is always the case for a first order system without the delay or any zeros. So that's actually what we have here. And that's again a confirmation, and that is actually what we have determined now using the Bode plot. So we actually use the simulation in the MATLAB. We have plotted the unit step response and a Bode plot, and in both cases we have confirmed that our transfer function for our system is correct. And now we will also look at this in real time in MATLAB, and then we will then discuss this in a little bit more detail, and you can see that also in real life. So let's jump to MATLAB. So we are at MATLAB. This is our command window, and this is the script I have prepared for this example number 3. Again, looking to the script, I have defined a Laplace parameter here by using this command s is equal to transfer function, and then using that parameter s. The parameters of our system, we have determined that the KDC was 6.51, so this is the DC gain of the system, or the steady state gain of the system. The tau, which is a time constant, which is then in this case 0.902 seconds, time constant of the system. And the model of the first order system was given by this, is KDC over 1 plus tau s. That's the expression we have here, and we have now determined the necessary parameters for our system. So let's run this and then check that also in the unit step response and also for the Bode plot and see what we have. So let's run this. I have now run this, and you can see that this is running. And I have now, let's check our transfer function h, which is given by this. So you can see 6.51 and over 0.902 s plus 1. I can also have it in a little bit different form, such that you can see the pole of the system. So I can do h is equal to 0 pole gain, so 0 pole gain, you can see this, and I have then this expression. Now you can see directly that the pole is at minus 1.11 approximately. So let's do then now the step response for this h, for this transfer function, also the Bode plot, and then we will see that we have the correct transfer function. So let's do that and agree on, and let's plot this. Now it will have some time. Okay, that's the unit step response. What do we see? Let's look at it and also show directly also the KDC here. So if I now do this steady state value, which is then in this case 6.51. Let me make it larger, you can see it. Okay. I can of course again check the points. So at 1 I need to have 4.36, in this case is 4.37, it's approximately the same. Of course you can go direct to that one if you just a little bit accurately. This all depends of course on the accuracy of your simulation, also on your calculations. At 2 I had 4.8. So those are, let me make it larger, you can see that better. So let me also make this larger. So you can see this is actually the confirmation what we just had. So this is correct, the steady state value on those two data points. So let's also check the Bode plot. So let me make Bode and then h and then grid on. And let's also check that. So this is the Bode plot. Let me make it larger. So this is the Bode plot. What I see is again the DC gain approximately is 16.3. Also make it larger. And you can see if I go down by 3 dB to determine the cutoff frequency, I see it is also that very close to the pole frequency, which is actually this one. So it is approximately 1.11 or 1.1. So of course you can do that a little bit accurately, then you have this one. Again, at the same frequency in the phase plot, you can check that this is minus 45 degrees, and you can see that this is also true. So that's actually the confirmation also in MATLAB. So that is what we have discussed in the calculations and also using the real-time discussion here in MATLAB. So that was our for example number 3 about a first order system. If you have questions or comments, as before, just let me know and I will try to answer them as soon as possible. Thanks again and see you next time. Take care, and we will continue, of course, with interesting topics, so keep in touch. Have a nice day.